second order differential equation. It has to have an exponential input, and there's a lot of little pieces to this that I probably won't be able to cover in class, so I figured I'd make this little video to give enough examples. So where we're going to start is we're going to be working with this differential equation, second order. Whether it's y or x, it's really irrelevant. So we have this general one, ay double prime by prime plus cy is equal to some input function. We're going to call it f of x. It could be f of t, that independent variables, kind of interchangeable. And one of my main mistakes is leaving x's when I really mean t's and vice versa. So what we're going to do is we're going to change it over into a differential notation. Remember, capital D means to take the derivative of. So here we have the function y, here we have the first derivative of y, here we have the second derivative of y. Alright. So if we look at this differential, we can kind of think of it as a function on its own. So we're going to take our differential, we're going to pull out the y, and look what is left behind is kind of like a polynomial with d as its variable, if you want to think of it that way. But it still is a derivative. So we're going to consider that a function of d, derivatives. We're going to call it this new p of d is equal to my derivative operator. And then this operates on another function. For instance, if we operate p of d on y, we come back to our original differential equation. Second derivative of y, first derivative of y, and y by itself, and then the a, b, c coefficients. So now we can take the entire differential equation and rewrite it as p of d operating on y is equal to our input function f of x. It's just a neat notation to make things a little bit easier in a second. Now we're going to be working with Euler's formula, and it works on this complex form of sine and cosine without the r coefficient out front. And Euler found out that the sum of these cosine theta plus I sine theta works exactly the same as e to the I theta. Derivatives are the same, integration is the same, their series solutions are exactly the same. So if we have input functions that follow these three possibilities, an exponential function by itself, a sine with or without the exponential function, and a cosine with or without the exponential, as input functions, this Euler method is going to work really nicely. So we're going to look at our differential equation, p of d of y is equal to an exponential input function. And I'm not putting the k there because it could be buried inside someplace. Alright, so we have this exponential function, and I want to see what happens if we operate p of d on the function e to the bt, the exponential, or the input function. So if we do that, and this is the long way of doing it, there's a shorter cut, but then I'd have to explain a few other things. So I just went and ground it out. So if we do operate the differential function over e to the bt, we're going to get the last term left all by itself, the derivative of e to the bt in the middle, and the second derivative of e to the bt in the front. Now when we take the second derivative, we're going to get a beta squared. When we take the first derivative, we're going to get a beta, and then this one's left alone. And all three terms have this e to the beta t, so factor it out. After we're done with that, we're down to beta squared plus b beta plus c, which is exactly the same thing as if we took beta and just substituted in for d to begin with. So this whole thing right here is just p evaluated at this number beta. Now beta could be real, or it could be imaginary, or it could be complex. It could be any of them. So technically we're just going to let beta be complex. Alright, so that's kind of nice. Now if we take this last thing and we divide both sides by p of beta, we're going to get a nice little equation here. And if you remember, this is the same thing as what I started with. I said, well, we have this differential equation, and we're going to let it equal e to the beta t. So that means that these two things must be exactly the same. That this y is or this e to the beta t over p of beta must be a particular solution to this differential equation, because it does equal what I had on the other side of my differential equation. So it's kind of nice. that's just elaborating it there. So it does imply that it is a particular solution to this nice differential equation that we started with. So this is a formula that we're going to use to find a particular solution after we solve for yp here. So we're going to find this exponential function up top. Sometimes we're going to have to play around with it a little bit. And then whatever that term or the number in front of t is, we're just going to plug it into the differential function and see what kind of answers come out of that. So for instance, a simple one, if we have x double prime plus x prime minus 2x is equal to 4 to the e to the 5t, then what I'm going to do is I'm going to set up a couple of things. For instance, the first thing I'm going to set up is p of d, because I'm going to use that later on. So this would be d squared plus d minus 2. So basically, it's whatever you see a double derivative, you just write d squared. A single derivative gives you a single d. No derivative at all, and you just drop off the x. So that would be p of d. And we could rewrite this differential equation as p of d operating on this x function is equal to 4e to the 5t. And then you can kind of think of it as the x distributes through this, and you get back to the original equation. All right, the other thing we're going to work on is we're going to have to write the particular solution. So the particular solution in this case is going to be the input function on top, and we're going to divide that by p of d. Now, or beta, I should say, beta in this case happens to be 5, so we're going to evaluate p of 5. So let's see, that would be 5 squared, that's 25. 25 plus 5 is 30. 30 minus 2 is 28. So this becomes 4/28 of e to the 5t, which is equal to 1/7 e to the 5t. And this would be a particular solution to this differential equation. The nice thing about this method is it gives us our coefficients, those undetermined coefficients, rather than going through linear algebra to come up with those answers, and systems of equations and all that fun stuff. So that's pretty neat. And of course we could do the characteristic and find the characteristic solutions of this. So we would have, r squared plus r minus 2. And notice there's, somewhat of a relationship between these two things. And we're going to set it equal to 0. And of course this is r plus 2 and r minus 1. This is a little review stuff. So this gives us a solution where we add together our characteristic answers and our particular solution. I'll put the particular first. So 1/7 e to the 5t plus c1 e to the negative 2t. That's from this one here. Plus c2 e to the t. And that's from this one here. And that would be a solution to this differential equation. Kind of neat. And notice this one, the input function is not an exponential, it actually is a cosine function. So one of the first things we're going to need to do here is transform this cosine to the 4x into its exponential equivalent using an Euler formula. Now Euler's formula has a sine and a cosine in it, so we're going to have to play around with our answer when we get to it. So I'm going to start it the same way. We're going to do our p of d first, and p of d is equal to, in this case, d squared plus 9. Nice simple one. And we're going to use our little formula to find the particular solution. And it's going to start off with this thing over p evaluated at beta. So I'm going to start off writing it as 2 cosine of 4x divided by p of beta. Okay. So let's do the little transformation. Now when we do this, it's going to introduce a sine and a cosine term. So we're not finding the exact particular solution anymore. We're going to have this complex particular solution, and half of it we're going to need and the other half we're not. It really depends on what function we start with. One half of it is going to deal with the cosine, the other half would deal with the sine. So when I write this, I'm going to split it apart, and it's not exactly equal to y of p, so I'm just going to designate it a little different. Yeah, put a little thing on top, a tilde, a hat, whatever you want. And then I'm going to rewrite the cosine as the sum of a complex term with the I in it. So I'm going to have this I sine of 4x included with it. And then, of course, this is going to be all divided by p of beta. Okay, so the top part can be rewritten using Euler's formula to be 2e to the 4i x. 4ix. So that just means that beta in this case is this 4i that's up here in the power. As long as the variable's pulled away, whatever's left over is the beta. So we need to take this 4i and plug it into p of d. So we're going to get p of 4i is equal to 4i squared, 4i all squared, plus 9. Now 4i squared, of course, is negative 16, and negative 16 plus 9 is a negative 7. So the number that's going to go in the bottom here is going to be negative 7. Okay. Now we want to get back to our original particular solution. We have to kind of get back to cosines. And since cosine is the real part of this complex part, we need to get rid of the imaginary part so we can get back to our regular cosine function. So when we think about this, 4ix is still equal to this mess up here. We just want the real part. So I'm just going to take off the cosine of 4x. So we can get back to our y of p is equal to negative 2/7, the 2 at the top, negative 7 at the bottom, cosine of 4x. And that would be our particular solution for this simple little equation. Alright, and then of course you could do the characteristic. It would be a bit of a mess because it would have complex parts, and I think it would be C1 cosine of 3x and C2 sine of 3x. Okay, let's do another example. As they get a little bit more complex, this one has a sine, 3 terms on the other side. That really shouldn't matter too much. So it starts off the same way. You do your p of d. We need that for that denominator. And it's going to be d squared plus 4d plus 5. And we're going to set up our y of p. And if you want, we can jump it right into the complex portion of it. So if we do y of p, and this is going to equal 3 times e to the it. I could rewrite this as sine or a cosine of t plus I sine of t. And then the complex part is the portion of this that I'm looking for. Of course, this is going to get divided by p of d. Well, in this case, d is just plain old I. So we come over here and we find p of I, which is equal to I squared plus 4 times I plus 5, for a grand total of 4 plus 4i. And I'm going to write it, since it has a common factor, I'm going to write it as 4 times 1 plus I. It makes life easier later, but not necessary. So I get this y complexified p is equal to 3/4, so I'll pull that 4 out front, times e to the it divided by 1 plus I. Okay. And what I need to do is I need to rationalize the denominator, get rid of the i's in the denominator. So we're going to multiply by the conjugate, 1 minus I, top and bottom. And when you think about this, what we're looking for is the imaginary part of the answer, because we're dealing with sine of t, which turns into that I sine of t portion. So the only part of this I'm really interested in is the imaginary part. So if you kind of imagine this as being your cosine and I sine, then the imaginary part is going to come from the inner and the outer of the answers. So we're going to get back to the yp, the particular solution. We have this 3/4 out front. We're going to multiply it by the fraction that ends up in the bottom, and we're going to get 1 plus 1, which is 2, so that'll be a half. And then we're going to have, let's see here, we want the imaginary part, so it's going to be the I cosine, so it's going to be cosine of t. And then on the, oh, wait a minute, that's negative, so it'll be negative cosine of t because of this negative sign here. And then here we got 1 times I sine, so that'll be positive sine of t. And then we can just neaten it up a little bit. Y particular is equal to, this would be 3/8, so negative 3/8 cosine of t plus 3/8 sine of t. And again, what's really nice is we don't have to figure out these undetermined coefficients. This method brings them into the answer automatically. Probably the trickiest example I could probably come up with, other than just being messy. This is a combination of exponential function and a sine and or a cosine. And here we're going to have to be a little bit more cautious because there will be 2 exponential functions that we have to deal with. Alright, so let's start off like we've been doing. Start off with the p of d function. And in this case, the p of d function is d squared plus 6d plus 13. And then we'll run into our formula which says, well, y of p is going to equal the function that we're given, the input function. This is sine of 3t. And we're going to divide it by p evaluated at beta, the coefficient of the exponential function. Alright, but again, it's going to be a little trickier here because we have the sine and the et function. So if I expand this out, oops, we can't call it regular yp, so now we're talking about the complex one. It's going to be 4 e to the 2t. The sine of 3t is going to become e to the 3it, but of course remember this is actually cosine of 3t plus I sine of 3t. So that's why we're calling it this new y function over here. Alright, if we combine these, all over p beta, we're going to get 4e. Base times base, we're going to add the exponent, so we're going to have 2t plus 3it, better known as 2 plus 3i times t. And then this will be over p of beta. Now beta in this case, of course, is going to be 2 plus 3i, which is a very messy, complex number to work with. Alright, so from here, I'd rather do the p of d first, so I'm going to go up there and plug it in. Let's see what happens. So p of 2 plus 3i. So we're going to have to square it. We're going to have to add 6 times it. And then finally add 13. After all is said and done, this is going to equal, let's see, 20 plus 30i. Just be careful of the square term, you do have to FOIL that all out. Of course, this is kind of messy, so I'm going to pull out a common factor of 10, and left behind is going to be 2 plus 3i. It's kind of cool if you think about it. Alright, so let's plug this back into our little formula over here. And we're going to have y's complex solutions is going to equal, I'm going to write it as 4 over 10, get that 10 out of the way. And then we have the e to the 2t. I really should pull him out of the way. And left behind is going to be this cosine of 3t plus I sine of 3t. And in the bottom, we're going to have that 2 plus 3i. And I need to multiply this to get rid of the complex number in the denominator. So I'm going to multiply top and bottom by its conjugate. And the part I'm looking for is going to be the imaginary part because we started with the sine function. So I want the things with the I in it. That's the part of the answer I'm going to look for. So if I want the I part, then this 2/5 e to the 2t is not going to change. If I'm looking for the I part, it's going to be this 2 times, let me do a different color here, back up. This 2 times I sine of 3t, and this 3i times the cosine of 3t. That's where my i's are going to come from, so it's the outer and the inner. So in front here, I'm going to write it as 3 cosine of 3t, and on the inner, I'm going to have this plus 2 sine of 3t. Okay. And that would be the I terms. In the bottom, we're going to have 4 plus 9, better known as 13. And then if we put it all together, we are going to get an ugly number. Let's see. 2 times 3 is 6. 13 times 5 is 65. So we'll get negative 6 65ths, e to the 2t, cosine of 3t, and then over here we're going to get a positive 4 65ths, e to the 2t, sine of 3t. And this would be the particular solution to this differential equation. And again, what's really nice is those undetermined coefficients just come right out of using this method. You don't have to go searching for them. And that's it.